Hello students, in lecture 21 of your course Calculus of Variation and Mechanics, here because we are discussing now the mechanics part. So in lecture 20 we have discussed the derivation of Lagrangian equation of the motion. In lecture 21 here we discuss certain applications of Lagrangian equation of motion. Particularly here we derive the equation of motion for a simple pendulum, then how to set the Lagrangian of a spherical coordinate system, and then in order to apply this Lagrangian of spherical coordinate system, we discuss the equations of motion of spherical pendulum. So here first example is set the Lagrangian of a simple pendulum and obtain an equation describing its motion. So from the diagram you can see, first of all you know that what is a simple pendulum. Simple pendulum is in fact a system where a small bob of mass m is attached to a string, and string is fixed at a certain point A, then it is allowed to oscillate like this. It is allowed to oscillate like this. And when we allow to oscillate it in this manner, it attains the maximum distance maybe up to point B. Similarly, the distance on this side may be up to the point, some point B dash may be there, B dash may be there. So such a system or such a motion is of a simple pendulum, and this is called a simple pendulum here. So like theta in this situation, what are the parameter or the things which are happening here? Theta be the angle made by the string AB, of the pendulum with the vertical AC. This is the mean position of the pendulum if it is here, and if it is here at certain point of time, and then this angle is theta with the vertical, and L is the length of the string at which in which this bob is attached. Now if we look at this distance from point B, then this distance will be something that will be calculated from this right angle triangle, and this distance DC in fact is the vertical height to which this pendulum goes at any point of time t. So here this is the height. Due to this height we can calculate the potential energy, and we'll also find the kinetic energy of this type of motion. And you already know the Lagrangian of a system is denoted by or is given by L equal to T minus V. T means the kinetic energy and V means the potential energy. So whenever we are talking about the Lagrangian of a system, two things we require: the potential energy V and the kinetic energy T. So these things we will determine from this figure. So let us see. Let L be the length of the string AB, then sine theta from the right angle triangle, this right angle triangle ABD, we can find the value of sine theta is R by L. And what is R here? R is this distance R, and L is the length of the string. So obviously this distance R will be variable in this case. So you can say sine theta equal to R by L, R equal to L sine theta, or you can say R equal to L theta. Why? Because for small change the sine theta can considered as approximately equal to theta. Because of that, here we are writing sine theta as theta only. When you take a derivative on both sides with respect to t, so we get R dot is equal to L theta dot, because L, the length of the string, will remain constant. So in fact here R dot stands for dr by dt, and theta dot stands for d theta by dt. So here we can see this theta is R by L. The kinetic energy T is equal to, you know, that half of mass into velocity square. But here you can see this dr by dt is in fact the velocity. So v means L theta dot. So you substitute it here, mv square. V square gives you L square theta dot square. So consequently, the kinetic energy is equal to 1 by 2 ml square theta dot square. Now you have to determine the potential energy V. And you know that if a particle is at a height h, the particle is at a height h from the ground or from the horizontal position, if it is at a height h and the mass of the particle is m, then the potential energy V is given by mgh. So this is the formula for the potential energy. Now let us see the situation in this motion of simple pendulum. At any point of the time when the bob of the pendulum is at this position, then in fact from the mean position it is at a height of this much dc. So the potential energy in this case will be mass of the pendulum, gravitational acceleration, and h means this height dc. So we want to determine this dc. How to determine dc? Dc will be ac minus AD. So you know AC is in fact L the length of the string, because we are already given L is the length of the string, so the length will remain same, so that is why AC is L. Now what about AD? Then from this triangle ADB we can have AD means base over hypotenuse is equal to cos theta. That means AD by L is cos theta, so AD is L cos theta. And you know AC is L, then you can say this DC is equal to L minus L cos theta. That is there, you can see mg equal to AC minus AD, that is equal to mg 1 L minus AD is L cos theta. So you take L outside, so the potential energy is equal to mgl into 1 minus cos theta. So now you have obtained the value of kinetic energy and the potential energy. Then of course the Lagrangian can be given by L equal to T minus V. So T is this quantity, V is this quantity. Now if we look at the situation here, we have to identify the generalized coordinates. So from the configuration, you see the configuration of system is determined with the help of a single variable here. And what is that variable? That is the theta, because here you can express r in terms of, because r is variable, but you can express r in terms of theta. So in fact the single variable theta can describe the configuration of this system. Therefore we have only one generalized coordinate here. That means we have Qj equal to theta and j equal to 1, means we have only one generalized coordinate, that is theta. Okay, so in place of this we can have, you know, this is the Lagrange's equation of motion in the generalized coordinate is given by this, and here you can see this is nothing here. So here you can see in place of this Qj dot we have only one generalized coordinate, that is theta. So this equation reduces to this form: d by dt del L by del theta dot minus del L by del theta dot. I think this is not theta here, this is not theta, and this is dot is not there in this case. It is so del L by del theta dot is in fact can be calculated from here. It comes out to be ml square theta dot, and del L by del theta we can obtain from this again, and the value comes out to be minus mgl sine theta, because cos theta derivative of this is minus sine theta, so minus minus plus, so this minus gives you mgl sine theta. You substitute the values over here in this equation, so we get d by dt ml theta dot square mgl sine theta equal to 0. Now here m and l both are constant, you can take these outside, You can take these outside and they cannot be 0. So derivative of this theta dot becomes theta double dot. In fact, meaning of theta double dot is d square theta by dt square. Fine. So here we are left with theta double dot, L will be there, and g sine theta. So you divide throughout by L, we get theta double dot plus g by L sine theta. But for very small theta, sine theta is approximately equal to theta. So that way, this can be replaced with simply theta. So equation we have theta double dot plus g by L theta equal to 0. In fact, it can also be written as d square theta by dt square plus g by L theta equal to 0. And in symbolic form, you can also write it as d square plus g by L theta equal to 0. So the auxiliary equation in this case becomes this. When you simplify, then d is equal to plus minus iota g by L. So these are the complex roots. The solution of equation is given by theta equal to c1 cos root g by lt plus c2 sin root g by lt. So that is how you have obtained the solution of this equation. So this gives you value of theta. Further, because you have obtained the value of the generalized coordinate, that is theta. So this gives you, in fact, the equation of motion. So based on certain conditions, these constants can also be evaluated, but here you can leave it at this place. So it gives you the solution or the equation of motion for the simple pendulum. Now come to example 2. Set the Lagrangian of a spherical coordinate system. Like for obtaining the Lagrangian, we require two things: the kinetic energy and the potential energy. Now we are talking about the spherical polar coordinates, so we should first know the relationship between the Cartesian coordinate and the spherical polar coordinates. Suppose we have, this is a three-dimensional system, and this is the point P, which is described by the Cartesian coordinates x, y, z. And if we consider that the polar coordinates are r, theta, and phi, where theta means this angle with z-axis and phi means this angle here, because when you are dropping this perpendicular from this point P, so here you can see that this is at L, so and this distance is r, then this angle subtended with z-axis is theta, and the angle with x-axis is suppose phi. Then we can get the relationship of these coordinates, Cartesian coordinates x, y, and z with the polar coordinates r, theta, and phi. In fact, x comes out to be this, y is this, and z equal to r cos theta. Now for such a system, how to obtain the kinetic energy? If you consider that P is the particle, then how to obtain the kinetic energy and the potential energy? Obviously, potential energy depends on the coordinates only. So you can say here the coordinates are r, theta, and phi. So you immediately say that potential energy depends on r, theta, and phi. So what about the kinetic energy? Let us see. Here the position vector of the point P is r, xi, yj, zk. I, j, k are the unit vectors. And we know the value of x is this, y, in fact something is missing here, this is our sine theta, and here it must have been sine phi j, and this is r cos theta k, right? Now if we differentiate this with respect to t, r dot means you are taking derivative of first and two are as it is, r dot same thing. Then you are differentiating with respect to theta, sine theta becomes the cos theta, and along with that we will have theta dot. So r cos theta, theta dot cos phi. Then we are differentiating with respect to obviously this with respect to phi. So when you differentiate with respect to phi, we'll have r sine theta as such. Cos phi gives you minus sine phi, so minus sine phi is there, and phi dot means d phi by dt t. Theta dot means d theta by dt. R dot means dr by dt. So that is how you have differentiated it with respect to all the three variables r, theta and phi, and you are getting this thing, and here is the unit vector. So this is a value of r dot, and this way we are calculating. Similarly, we differentiate here with respect to r, theta and phi. We'll get this term, second one. And when we differentiate with respect to r and the theta here, because phi is not present here, so we'll get this term here. So now if r dot square is calculated, that is r dot, and you will take the dot product. And when dot product is taken, r dot with r dot, what we get? We get this term multiply with the same, we are getting the first one, plus this with the same, we are getting second one, and then this with the same, we are getting the third one. On simplification, we obtain this value. We obtained this value. And the kinetic energy, you know, is given by half mass into velocity square, because you know r dot square means in fact r dot means the value is dr by dt, and it's square. This is in fact the velocity square. This is in fact the velocity square. So when you put this value, so this is the kinetic energy, half into mass velocity square. But this r dot square gives you this value. This is value of in fact r dot square. You substitute the value here, it is this. Arrow will not be there. Arrow is not there. This is simply r dot square plus r square theta dot square plus r square phi square sine square theta. So that is how you have calculated the value of kinetic energy. And the potential energy, obviously it depends on the coordinates only, r, theta and phi. So we'll write this expression as such. So the Lagrangian of a spherical coordinate system is equal to L, is given by L equal to T minus V. So T is this quantity, half m r dot square plus r square theta dot square plus r square phi dot square sine square theta. Let us see, phi dot square sine square theta. So here we'll write phi dot square sine square theta. So that way, this is the Lagrangian for a spherical coordinate system. So let us apply the situation and some practical problem. The third example is set the Lagrangian of a spherical pendulum and obtain an equation describing its motion. So what is a spherical pendulum? In fact, in a simple pendulum, you are attaching the string here and you are allowed to, the bob is allowed to oscillate in this manner in a plane. But in a spherical pendulum, we are fixing the string here, and length of the string is L, and this is the bob of the pendulum of mass m. It is allowed to oscillate in the whole space like this. So when this is oscillating in this manner, not only in the plane, it is oscillating in the space like this. Okay, so the angle is theta, of course, with the vertical, and the simpler type of configuration we are providing here, this is the angle phi. So you know x value of x, y and z in terms of r, theta and phi, as we have calculated earlier. You will see that in this case, the r is L. L, that means is constant. So accordingly, this whenever you will have r dot, then definitely this is 0. So that means we will be left with only two variables theta and phi. Left with two variables theta and phi. So accordingly, we can evaluate the value of kinetic energy and the potential energy. So you can see a mass m is suspended from the ceiling by the string of length L, as in the plane pendulum. Now, however, the mass is allowed to swing in all direction, means it is swinging in all direction. The situation is thus the same as mass constrained to move on the surface of a sphere, with gravity g acts vertically downward. Let us again use the Lagrange's method to find the equation of motion. So first we should identify the generalized coordinates. So spherical polar angles theta and phi will be the generalized coordinates, and consequently the kinetic energy is obtained in this manner. How this comes out? Let's recall the example 2. Here we have obtained the kinetic energy as 1 by 2 m r dot square plus r square theta dot square. You can see plus r square and phi dot square sine square theta. You see this, verify r dot square theta dot square r square phi dot square, that was there, the value of in fact the value of kinetic energy 1 by 2 m r dot square theta dot square and this quantity. So if we compare the situation here, the r is L, r dot is 0, so this part is 0, and here we are left with L square and L square. That L square is taken outside, 1 by 2 ml square. What we are left with, theta dot square plus phi dot square sine square theta. So this is the value of kinetic energy. Now if we talk about the potential energy, now potential energy is of course this height, this is the height here, and it can be obtained H is equal to L cos theta, and potential energy is mgh, so V equal to mg L cos theta. So this is the potential energy. When we substitute it over here, and definitely because we are talking about because the coordinate system is here, so we are talking in downward direction, so this is, we can consider it as negative. So at t minus v means it gives you plus mgl cos theta. So this is the potential energy and this is the kinetic energy. It's a derivative. Obviously we have identified here that the generalized coordinates are q1 you can consider as theta, q2 you can consider as phi. Only two generalized coordinates are there, so that means we require two equations, Lagrange's equations. Two equations will be there, d by dt del L by del theta dot minus del L by del theta equal to 0. This is the first equation, and the second equation will be d by dt del L by del phi dot minus del L by del phi equal to 0. Using these two equations, we can obtain the desired equation governing the motion of a spherical pendulum. So we are obtaining del L by del theta, then del L by del theta dot, substitute the values over here. And further we obtain del L over del phi and del L over del phi dot. Values comes out to be these. These values are substituted in these two equations. Consequently, we get these equation, this equation and this equation. So here, these are the equation that governs the motion of a spherical pendulum, or you can say these are the equations of motion for a spherical pendulum. In this example, you can notice that Lagrangian does not contain the generalized coordinate phi. You can see the Lagrangian is here. Here we have theta dot, phi dot, theta, but we are not having phi. So when such a situation exists, such coordinate is often known as the cyclic coordinate. So in this case, phi is basically the cyclic coordinate. Physically, the reason for this is that system remains unchanged under rotation about the vertical axis. The system is invariant, or you can say the system is invariant under these rotations. The Lagrange's equations then imply that the generalized momentum ml squared sine squared theta phi dot associated with phi, which is physically the angular momentum in the vertical direction, is constant of the motion. So we say the angular momentum is conserved. The angular momentum is conserved. So this is about the motion of a spherical pendulum. So that is it about this lecture. Thank you.